All right, hey everyone, I'm David Room. We're gonna get started here in just a second. I've got some exciting stuff to work on tonight, and it's gonna be kind of an intense stream. I'm gonna be doing some 3D mesh processing with Python, and gonna be working on something a little different than what I usually stream on. So a lot of times I do kind of low detail sketching out of different 3D models. Today we're going to do some high detail greebling of a spacecraft model that I've been working on using Python and Blender, and I'm gonna definitely have to crank through and probably update some things that I've built in order to get done what I want to get done today. So, and you know, when you have these personal projects, and like this project I've had for a couple of years now, you kind of work on one thing at one time and then go back to another thing. And I've been kind of working on game development for a while recently, but I wanted to pivot back and hit the whole high detail aspect of my project for a while. So the high detail part is an aspect of the project where I'm taking these kind of low poly ship designs and I'm turning them into higher detail models that are appropriate for more realistic renders, and specifically rendering them in Blender versus rendering them in a game engine. And this stuff actually goes back to I think 2021 in the I think 2021 in the uh, wintertime. And in classic 80-20 rule fashion, I thought I had a lot of things figured out then. But since then, I've figured out a lot of different ways of doing things, better ways of doing things, more efficient ways of doing things, more correct. I learned that kind of high poly 3D modeling in Blender is a lot harder than it seems. You can't just do a bunch of Boolean operations and expect things to work nicely. So we're going to be revisiting some of that, and there's definitely like functionality that I have and I know that I have, but I'm going to have to rewrite it to get it to work like I want it to work now. So we're going to get into some of that today, and I'm going to show you what I'm trying to do. I think it's pretty interesting. I think it's pretty interesting stuff, and at any rate, it'll make for a good live stream hangout time. I might go a little longer than usual tonight. Might not be too chatty because I'm going to be thinking. I've got my notebook and a pen out because I'm almost certainly going to have to write some stuff out to solve some problems. But I've got my coffee. I've got some cold water. I'm feeling pumped, and I hope that if you're watching, even if even if programming isn't your thing, or this specifically what I'm doing is your thing, I hope that you'll hang out and spend some time here and be encouraged in whatever creative projects or programming projects or whatever you're working on in your life. That's my part of my goal with these live streams is to kind of be a friendly face to people who might be working by themselves on creative projects. I know that's something that I really enjoy about some of the live streams that I watch, is just that kind of camaraderie from knowing that other people are out there doing cool work. So let's get into it. I've got a new desktop share aspect ratio here. I have a MacBook Pro. I was always doing kind of something that ended up leaving a lot of black space at the side. I'm trying to zoom in, so we're missing the dock and the menu bar, but there should be more code, and I don't think the menu bar stuff is that important, so we'll see. Yeah, so let's get into it. So I've been working recently on a ship in my fleet, and I have this sci-fi project, and I have this game where I'm building this fleet of ships, and kind of developing the designs and stuff. I have this ship called Ashinoko, and I'll just run my workbench here, and we'll generate it. So I've kind of showed this before, but I have in a module, I have like one module for each ship that I'm working on. Oh shucks, the desktop share is doing that thing where it's not actually sharing. Oh, son of a gun, why is it doing that? I'm glad I caught this. Let me stop streaming and start again and see if that fixes it. Oh, son of a gun. Sorry guys. I'm gonna restart OBS and see if that fixes it. So I will be back in just a second. Okay, I think we're back. Sorry about that. I'm glad I caught it. I'm glad I caught it though. Yeah, I don't know why that happens. Okay, so getting back here in the mood. So we've got the Ashinoko, we've got a module, Python module for it. We have both the high detail and low detail version. And actually, why don't I start just with showing you the thanks, Doug. Yeah. Thanks for sticking around. So I'll show you the low detail version first. So this is kind of what the low detail version is, kind of what goes into the game. So hopefully this still works. I haven't tested it maybe recently. Okay, so this runs, and here's the low detail version of the ship. It still is about 3,000 faces, and I think that's due to mainly those faces add up in the circular areas and stuff. And actually this little this docking ring has quite a few. But something that I think helps 3D models to have a good sense of scale is when you have areas that are kind of high detail and low detail. So okay, so, and let me just, yeah, cool. I think this new desktop view is going to work a lot better. So, and a couple other views, we're building some new ways of viewing 3D meshes the other day. And what this looks like in the game engine, and this might not be the most recent version of it, but in the game engine is going to look like this. So kind of a nice low poly look. But what we want is we want to be able to kind of take the same design and add greebling and details and things to it and make something that we could render in a more realistic way in Blender. Let me actually just show an example of the kind of image that I'm talking about. Hopefully this won't make us lose the desktop again. I don't think it will. So yeah, earlier this year I was working on this other ship called the Scioto, and here's a render I did in Blender of that ship. So this is not this is far from complete. There's still a lot of details missing, and needs improved materials and things. But this is the kind of thing that we're working towards. So let's take a look at the high detail Ashinoko. And whoops. So it takes a little bit longer to generate, but actually not too much. I've got some debug views here. And this is some functionality that I'm experimenting with for interactively looking at the panels that I'm slicing out. And the idea here, I just built this functionality the other day, is the idea here is that in this method you kind of slice the part into like a number of rings, and then each of those rings has facets that you can kind of identify by their sorted order and merge together into different panels. And I was in the middle of doing some of those merges, so we're looking at some debug info. So this is what the end result looks like currently. I can build some functionality here to do this ring slicing in a different way that will make it even more flexible. I'm not going to actually look at that tonight. Tonight I want to look at something different. So yeah, this is kind of like the in progress greebled version. So there's a few different things we might work on tonight. One thing we might do is add the same kind of paneling, like greebled paneling, to the drives. I think that isn't going to be isn't going to require too much messing around, so I'm going to probably save that for another time. What I want to work on is a couple other things. So for one thing, there's been this ongoing issue with the high detail approach, which is when you have little parts and then you add these panels, the little parts need to be adjusted so that they pop out a little bit, right? So like if we pull off this panel, you see that the parts are sticking up and are placed appropriately. So when we add this panel on, we need to appropriately raise these pieces up. So like this piece needs to come up, this little hard point like turret mount thing needs to come up straight vertically. The shield ring is orientated so that its z-axis aligns with the normal of the plane, so it needs to come up in that normal direction. So I might build something that makes that adjustment for these different parts. I think that is not going to be too hard to do, but it would be good. So we might warm up with that. And then the other thing that I want to do is I want to add some details where I basically find where some of these things are, specifically the hard points, and I add some detailing into the panels around them, because that's where it would make sense to have detail like that, maybe like sort of impressions, or like I thought it would look good to have like circular, not cutouts, but sort of like indentations in the panels. And I have this nice workflow where I can add greebles to panels constructively rather than doing mesh booleans. You just kind of have to figure out where things go and like think around with the coordinate systems and stuff to get that figured out. So and part of that is like transforming through different coordinate systems. So like if I know, like I know this part is here in the part hierarchy, so I want to find like the spot on this part that's related to a certain coordinate in this part's coordinate system. That's kind of tricky, because this I don't want to make assumptions about how this part is related to this part. I just want to be able to say, find the panel that is closest to this part and, you know, identify things properly. So that's what we're going to work on. We could also do high detail radiators, but again, that's kind of not too hard of a project, so we'll probably save that for another time. Oh, and looks like yeah, these dishes also need to be high detail. Oh, and this too. Yeah, a lot of this stuff is actually not high detail. Let's fix that docking ring first, actually. So that actually should be not too hard. Docking ring new 1. So this equals 1. It's just kind of a little hacky thing that I was doing here. Good, and it looks like my thing is working. So, okay. So I think this should fix the level of detail in the docking ring. Oh, and I need to disable some of this stuff too, because we're not working on this right now. Yeah, that looks better. There's a lot more detail in the high detail version of this docking ring. And I don't know if I have high detail versions of those dishes. It seems like I should. Yeah, that's weird. Maybe LOD just doesn't do anything here. Yeah, that's what's going on. So actually, let's just fix this quick. So LOD again is the kind of description of a level of detail, and -1 is the high detail version. So let's just bump this stuff up, and we will move this up to the top here, and we're going to add another So let's see here. This could probably, doesn't have to be super big. And this is the fun thing about doing stuff programmatically, is you get these things for free. Yep, look at that. A little bit too thick maybe, but not too worried about it for now. let's dive into the offsets first. So how do we want to do this? So we want to have, I think, we want to have a general function because we can kind of do this in one go. Where we adjust other parts with regard to the panel thickness. And I want to see it. So like parts to adjust equals, use a for comprehension here. In items, if, and there'll be multiple conditions here. Okay, that starts with sensor, or it starts with shield, or starts with hard point. And let's just take a look before we run this if this looks like what we expect to see for this list of parts. Let's do keys, and we'll exit here. And this will also give us a chance to get rid of those extra views here. So that, and this is a PV. It's this one, I think. Whoops. Actually, we want to get rid of the call to this guy. So debug is false. So this is kind of what the code to do that panel splitting and merging looks like. There's a lot more hard-coded stuff here than I would like, but sometimes that stuff is unavoidable when you're doing a complicated shape. And I think it still does work pretty well, and there's still a lot of advantages to doing stuff programmatically, even when you're hard coding things versus not. Okay. So yeah, hard points, shields, sensors. These all look basically like exactly the things that I want to move. So what we want to do now is we want to adjust these parts according to the inverse. Let's see here. Yeah, we want to adjust them according to the transformed z-axis by their own transformations. So we can just go through V in here and say transformation dot translation. So can pull that out. So we'll just call that translation. Then we want to actually we can just pull out the rotation too, just for the sake of it. So the rotation is basically the rotation of the part in the coordinate system of its parent. And the rotation happens first. It's like the part is rotated and then moved into like to the translated point. So what we want to do is we want to local, let's see, we'll call this Z local is mu dot rotate. We want to rotate the vector by that rotation, local, and then actually we don't really need TL, so v.transformation.translation plus equals z hat local times panel. Oh, I need to make the panel thickness a constant here. That is over here. For x, chamfer height proc is just this. So all of the panels on this ship are 0.2 meters thick, so we want to translate everything up by 2 meters. Now this isn't going to be exact for certain things that aren't exactly facing the same direction as the panel normal, but that's okay. I think this is still going to do what we want, and it's going to be close enough. So let's try it. Z hat local panel thick. Actually, yeah, yep, that's what we want. And there's other ways that we could write this too. I could also find the thickness first and then transform it, but I think this is a little bit clearer. Okay. So yeah, let's see if this works. And we can get rid of this now. So we'll just add a comment here. Will it work? Oh, nice. So Jupiter BJY is here. We've talked a lot in comments. It's really cool to see you here. And oh, nice. You're skipping out on work today. That's fun. Yeah, so I'm just if you're just catching up, so I'm doing some higher detail modeling of these versions of my ships that are kind of like the low poly version with added details. And I'm working on adjusting components to compensate for the thickness of the panels that things are attached to. So yeah, so one thing I thought I might run into here is the case where the rotation is not defined. So like if the transformation dot rotation is not none, then it's this. Otherwise, we'll just use the identity here, like this. And oh, did I misspell it? None type, yeah. So this is also, we gotta check if transformation is none. If v dot Information is not. Yeah, the panels are not hard coded. There's like a certain actually, yeah, we can skip through here. We can actually just, yeah, the there's certain aspects of them that are sort of like intentionally specified, but then I'm also trying to build tools that automate a lot of that. But like what I don't like is you see a lot of things like Blender add-ons where they just kind of like automatically make a spaceship that looks kind of random and jumbled, and that's not what I'm trying to do. I'm trying to make things that seem like they have a purpose, but then also I'm creating them in such a way that I can kind of scale and reuse pieces and things as I see fit, and um, you know, I have control over things. I can make things look intentionally created rather than random. So let's see. I've got to handle the case here where a translation is none. So in that case, I think it's just going to be, yeah, I can just capture that. So, and I think, yeah. I was talking the other day about how I need to rework this part. Equals this. Okay, let's see here. Type is not none. Oh, is, and this is none. Oh. I'm gonna fix this logic later. Transformation is none. This is gonna be the same thing. Okay, and yeah, then if we need to make a new transformation, if is none, transformation equals p stop translation. There we go. And did we do it? Yeah, we did. Look at that. Maybe not quite right. Yeah, so it looks like we've got some of these that are sticking up more than others, unfortunately. So maybe not getting quite the right coordinate system. Yeah, it looks decent, but we want to be adjusting things out by like whatever the let's see, am I thinking about this right? I think, yeah, by like, maybe do I want the parent? No, I don't want the parent. Oh no, I do, because these guys are parented not to the panels. they are parented to the fuselage. That is what is going on here. So I do actually want to... Huh? I want to transform them by their... isn't that what I'm doing? I want to transform them by their own rotations. Interesting. Okay, something is... This is the kind of the fun thing about this stuff, is you always run into things that are a little bit unintuitive. And maybe I just have a stupid maybe I just have a stupid bug here. But let's see here. Let's see, local. Is it the... Let me just print some of these out and see if I'm thinking about this right. So actually, I've got a good idea here. So we should be able to see, if we grab all of these, the XZ coordinates, and plot them, we should be able to see what's going on. So XZ before is... and I think what I'm going to do is I'm just going to go through here and add identity. Well, let's see here. No, this isn't going to work because I'm finding... it should still work. Actually, what parts have identity transformations? That's a good question. Stop values. I'm going to investigate this here. Something isn't quite adding up here. Oh, that there's the problem. I was adjusting all the parts, not just the parts that I wanted to adjust. I bet this will fix it, and I bet I can get rid of a lot of that logic too, because none of those parts should have... No? Son of a gun. All right, I'm really curious about what's going on now. That was definitely a big bug. So what gives? Okay, let's take a look at this. Yeah. Yep, and that's why these things are useful, is they'll catch things like that. Yeah, okay, so I should be able to plot these and get something useful, I think, because almost all of these I think should be parented to the fuselage. Let me actually just check that. Okay, so I do have those things, but these things I think it shouldn't matter. Um, what I'm thinking about should still work. Okay, so let's do some plotting here. So xz4 equals yeah, that's exactly right. So Blender is being used to test the code for model generation. I have a library by which I can send a hierarchy of 3D parts into Blender for viewing, and it allows me to debug things and interact with things and see where things are. I actually have a process too where I can do that interactively, so Blender stays open and like reruns a section of code that I'm running and refreshes the model, but it actually ends up it's just so fast. Just Blender's so amazing. It's so fast to load that I end up like not really even needing to do that. It just loads right up. So yeah, once the process finishes running, I load it into Blender and then I can look at things. So let's see here. So I want so let's look at these. Before and after. Whoops, missed. Okay, let's see here. Interesting. That is interesting. And what? Which of these parts has a none? Oh, has a none transformation. Oh. I know what's going on. I know what's going on. And this might actually be the. This might actually be the. That might actually be the bug. Let's see here. I'm gonna print the names again here. List of parts. I think I might have still been selecting a set of parts that I was still ending up shifting the whole thing. And that, yeah, that would explain what I'm seeing, because things were being, like the whole set of parts was being shifted up. So let's take a look at this. So, whoops, not values, keys. Yeah, so I had added those back in. See, without these, I think we're getting the whole set. There's like shield, yeah, shield, yeah, it's hiding in there. Shields and sensors are like parents that hold things. So at least shields would have been screwed up. I don't see hard points or sensors in here, but I think this might actually fix it. But we should see some, there's gonna be some cool visualizations here anyway. So yeah, so there's the XZ projection of all of those parts. Yeah, and you can see there that everything is getting shifted a little bit, but the question is it the right direction? So I'm going to do one better as long as I have a nice way to do this. I think I do. Sex 2D, and let me just refresh myself on what segments is here. I have a bunch of little wrappers around matplotlib because I can never remember how it works. Segs 2D, yeah. So segs is a tuple. Is that what it is? Yeah, it looks like it's a tuple. Yeah, okay, let's just try it. So if we zip yeah. And unfortunately, I still can't tell which which ones come before and which ones come after, but that's okay. I think I'm frankly going to be surprised if this isn't actually correct here, because I think that little bug explains why we were seeing some things not working. Yeah, this looks much more correct now, because yeah, everything looks like if we look at it from the front, everything looks like evenly spaced here. Yeah, so Jupiter BJY, do you use PyCharm or VS Code? I love PyCharm, and there's been a couple things that I've had to use VS Code for in my day job, and it's unbearable unless you install the PyCharm keyboard shortcuts. But even so, it doesn't work. It doesn't work as well. Yeah. Okay. Well, so we got that working, and that looks pretty cool, if I say so. Let's say so myself. Now there's a couple other things that we want to adjust here too, which should work basically automatically. There's a radar, a couple of radars that are hidden in here. So I think if we get the radar prefix, that'll grab those and docking ring. So let's add those, and we should see the radars pop out. Yeah. I had a friend who does a lot of coding in Vim, and with the right plugins, and like if you're good at keyboard shortcuts and stuff, that works pretty well. But PyCharm is really fast, you know, like the searching once it indexes things is super fast. Even works good on like actual spinning disk hard drives. I mean, it's extra fast here, but you know, I've used PyCharm a lot on a lot older, less performance systems than this one, and it still worked great. So Jupiter BJY says VS Code was quite better than expected with a bunch more plugins. But Visual Studio, yeah, double shift and everything, even settings being searchable. Yeah, I think you can search settings in VS Code. Like I've for my job, I've started to use VS Code for one project just because that's what everybody has like all the plugins and stuff configured for. It's actually for C++, not for Python. But yeah, you could. I think you can search settings, but you know, like actions. Like one thing that's really cool about PyCharm is like you can search actions, and one thing that that is cool about that is like when you like say if you record a macro, you can search for it by name, so you don't have to make some keyboard shortcut for your macros to be able to use them. You can just search for them by name when you need them. Like I have a macro called that's called move to top. So I can just search for move to top and run the macro, and I don't use it all the time, so I don't have to assign some extra keyboard shortcut to it, but I can find it when I need it. Yeah, the double shift to search, and like it's, you know, it's everything, right? That you can search. That unified search across everything is really cool, and it's fast. It's fast too. Okay, so I think we can comment out all of this stuff. So we've got our greebles adjusted out by panel. Oh, I was going to add the radars. And the docking ring. Oops. Let's see. Just make sure that this gets all of them before we go on. Yeah, and I mean the thing with VS Code too is it's, you know, it's designed to be like this Electron thing where you have to add plugins to get what you want. There was another editor before VS Code called Atom that worked a lot the same way. I don't see my radar dishes. And I mean, what's nice about PyCharm is it's just all there right out of the box. Like I think there's maybe 1 or 2 plugins that I've added. You know, 95% of it is there, and like even settings are just what I want. Like there's a couple of settings that I change. One thing I do right away is I enable scroll wheel font size changes so you can zoom in and out, and just some little stuff like with like trimming trailing white space and stuff like that. But overall, it just kind of does everything that I want right out of the box, and it's hard to argue with that. Okay, so what's going on with my radar? Where's my radar? Yeah, okay, so yeah, and that's exactly right. Yeah, maybe such are what makes IDEs different from multipurpose text. Yeah, exactly. PyCharm is intended for Python, and you have to use a different JetBrains IDE if you're going to do C++ or Java or whatever. It's not a general purpose IDE. It's like it's an IDE for Python. Okay. Let's see. What do I call? Oh, no, that's the radiators. Array. Oh, it's fuselage for some reason. Radar. Okay. Yeah. Yeah, so you're wondering about the hard points. Yeah, so the hard points are the square things actually. The hexagonal things are shield rings. So the in my fictional universe, um, basically there's like these magic devices that are can like do reactionless thrust and generate shields and also do like artificial gravity, and they use spinning rings. So pretty much all the devices that do that kind of stuff are somewhat ring shaped. The these triangular things are thrusters, and they're still low detail. So like actually high detail version of this, it's kind of like a delta shaped thing that would have like um, three separate like mini thrusters in it that are pointing off in each direction. So that's like each of those would have that. And these are the hard points. So, and there's a system in my we're not we're just going directly from parts into Blender here. There's a system in my games like data structures for putting weapons onto hardpoints. So like if you run the ship viewer for the game, you'll see that is that like the different guns are or turrets are mounted on those hardpoints. Yeah, and that's why there's no visible exhaust on thrusters or actually on the main drives. So something I've been playing with for a while and is kind of another big thing on my backlog is I think I it just needs a little bit more visual interest. So I think I'm gonna add like some kind of like slits or openings to the back of the drives that have sort of like a faint glow on the inside. The idea is like that these drives are like they have these the way it works is that there are like these spinning rings that have like a whole bunch of relays on them that just run like open and closed really fast, or maybe have like different patterns of noise that if you like run it fast enough and run enough electricity through them, like they're super high voltage and the whole thing spin really fast. The idea is that it kind of like it generates this weird entropy effect where the official explanation for how it works is like the universe kind of can't keep up with the the motion because it's like so unnatural. So you get like this gravity warping effect, and with the drives it ends up kind of like creating this flow um, that makes them sort of behave kind of like propellers on ships rather than rocket engines. And basically like the my setting, it takes place in the solar system, and the whole solar system is like full of this invisible stuff that to these engines is kind of treated like water. um, but there's also an effect where the faster you're going through it, this you can like dump more electricity into the drives, so you get that like constant acceleration effect. It's very convoluted, and I need to write it down. But if these things do act like propellers, it would make sense for them to um, it would make sense for them to have some openings sometimes. Like there might be different designs, like to this sort of magic drive. A lot of things are like functionally transparent. Like you don't necessarily. Oh, that's too bad. Oh, I know what's going on. It's because the radars are actually not oriented in Z. Yeah. Yeah, I'll work on the radar some other time here. But it would make sense for certain drive designs to have openings that kind of would allow more flow. The way I kind of explain different chip designs is like that there's sort of a some trade-offs between good flow for your shields versus your drives. So there's like inefficiencies in maybe how you would place antennas or shields or weapons or whatever, and that kind of leads to different different chip designs. And might explain things that look cooler and less practical. Okay, so yeah, and I'm just gonna leave it some notes here for me to clean this up. Okay, so what we're gonna do now is dive into something a little bit more intense, which is greebling on the panels. And I'm gonna review some code that I wrote before because it's been a long time since I've written it and I've kind of forgotten exactly how some of it works. But basically the idea is that we're going to try to add greebling to the panels in proximity to the certain things like the hard points. I want to do like some circular cutouts or indentations, or like I could do circular cutouts or panels or details near the shields. So there's the problem of kind of relating the coordinate systems of different parts together and stuff like that. So I'm just gonna close a bunch of this and review how some of this worked. So yeah, so I've got this functionality for doing booleans against panels, which I don't want to do here. I want to use a different workflow that doesn't involve booleans, but there might be functionality in here that I want to reuse. So this is letting us, so parts is like my personal model hierarchy, which is like just a dictionary of parts. And yeah, we find the global transformation, diffing, okay. And then let me look at this. So this is all stuff, like this whole process kind of is always working in the coordinate system of the panels. And you know, what I want to do is I want to relate points that I'm finding globally to points in the coordinate system of the panels. To be able to do this. And let me look at another one. So this is actually a bunch of stuff that I did last summer that I barely I barely remember now. So basically the process is like if you have a panel, you put it into a nice coordinate system, and then you can take the bottom and top part and add like geometry for the different greebles, and then sort of, because it has nice properties, you can kind of retriangulate everything and put it back together. And so like you have like your bottom of the panel, you have greebles, which are like the little meshes for the different parts that all have an edge, and what I call the gasket, which is like connecting the top part to the greebles, and then you put it together. And let's see here. Find vertices. Yeah. So I've got a bunch of stuff in this module called decal for like, here we go. Here we go. This is what I want. Find proximity parts. Points, distances, and normals. And I should be able to, yeah, because like this is operating in the global space. I should be able to find these closest points, and then using the global transformation of that part, invert the transformation and move those parts into the local coordinate system of the panel, which is what I want. Yeah. So it Jupiter BJY says retriangle without blender sounds quite complicated. Yeah. So originally when I was doing this, I have a method where I was like adding detail with booleans, but the problem is there's all kinds of cases where booleans fail, and they're also slow. And most of the things that I was trying to do, you can actually do without booleans, just by building up the data structures. Actually, let me see if I can find I should have some images of what this looks like. Let's see if I can find it. Yeah. Okay, so this is what it looks like. So yeah, I was working on this actually about this time last year. So you can, like, if you have a panel and you have, so this panel is like, there's like a bottom, it's a manifold. There's a bottom, sides, and a top. If you can identify, pull out the top, then you can do slicing or different things, and you can make a gasket. You can like chamfer things, and then basically concatenate everything back together. And I think the next month here I kind of take this to another level. Yeah, pretty proud of this stuff. Yeah, so like you can cut out the top, you can chamfer it, you can raise it up, and then you can like build that gasket where you triangulate everything back together. As long as it kind of makes sense in 2D, that's sort of the main thing, is you need it to be 2D to do the triangulation. But then it works. And usually you can do this stuff in 2D. So you can do these nice details, and you can even do details on curved panels constructively, which is pretty cool. Let's see if there's and you can add little details and things like that. Let's see if there's any more. I think I went on and was doing other non-high detail. Oh yeah, yep. And here's like another example of it. So you can like build these rings, chamfer them, inset them, and then if you build a list of them, then you can triangulate. You can kind of trivially triangulate through them to build solids that have holes or whatever. Yep. Is this all done in pure Python or with Blender? It's all done in Python. So it's not, I wouldn't call it pure Python. I'm using numpy, obviously, and the trimesh library for some stuff. I think the triangulation is done with Shapely. So there's aspects of this that I didn't write. Shapely, yeah. There's aspects of this that I didn't write myself, but generally the process of like building the different objects and stuff is not, it's not using Blender. I'm just viewing it in Blender. Okay, so I think we have, trimesh Shapely. So trimesh, I don't know how much of this kind of stuff that you've done, but I think trimesh, I have issues with. It definitely does a lot, but I think it's kind of a, it's not, the way it's designed is very object oriented. Like when you have a mesh, it has like all these additional things attached to it, which are not, like, I don't like that. Like, to me, a mesh should just be a mesh. And then if I'm doing some operation that involves other data, I don't need the mesh object to cache it, but trimesh does. So the way I use trimesh is I'll just do a conversion for something specific and then toss it or convert back. For me, a mesh is just 2 numpy arrays and that's it. Yeah, it's odd. And I mean, I understand why they do it, because it makes it kind of foolproof to do crazy mesh processing stuff efficiently, but that's just not the way I like to write code. I don't like things being cached invisibly, and there's also weird things that trimesh does, like by default when you create a mesh, if you don't do certain things, it will even like do a bunch of processing on it. So like I have just so you can see, so like my mesh type is just literally a tuple of 2 numpy arrays. I don't even have fields, just because it's ubiquitous. Like when you make a trimesh, it's like the constructor takes vertices and faces, but you have to tell it process equals false. Otherwise, it'll like totally rearrange the order of your vertices and do all kinds of crazy stuff. So just by default, it's doing all this weird stuff that I don't like. Someday I gotta write my own concat function, because it's kind of should be a pretty trivial thing to do. And I generally, the more I use trimesh, the more I want to get away from it. Definitely useful for certain things, but certainly there's things that bug me about it. Okay, so if we bring back up that decal module, so this is the function that we want. So we want to basically do something where we do this, but we also want to find, we want to do this, but we also want to find which which part that this belongs to. So this isn't quite what we want. Let's see here. It wouldn't be the end of the world just to write something fresh, because chances are whatever I have is out of date and not quite what I want anyway. Yeah, like this diff and mesh against multiple meshes thing. This all needs to be rewritten anyway. Yeah. Let's yeah. Yeah, it definitely I would say that's a good way to describe it, as violating the principle of least astonishment. It's like an attitude that once you put your data into their object, it's like it's sort of gone. But like that's not how I program. Like when I construct an object, I sort of assume that nothing is happening to my data. Like if I create an object that has certain fields, I expect those fields to just be what I put in. And I think that makes more sense. Okay, let's see. Do I have something in here that structure? Do I have something in here that actually finds which mesh is the closest? I don't think so. Yeah, I think the other stuff is actually all find proximity all. I don't know what this was even being used for. Yeah, I can just get rid of this. It's closest point. Sections. Yeah, I don't think I need raise because I'm not. Let's see here. Yeah, I don't think I need raise. I'm interested in just finding the closest point, and normals is fine. So we're gonna do a new version of find proximity parts that instead of just returning points, distances, and normals, actually returns the part that closest point belongs to. Okay, and let's set up a little bit of a test or something for this. Yeah, Zen of Python line 2, explicit is better than implicit. I do believe every Pythonista should prefer actions being explicit. Yeah, exactly. Now, the problem with Python is that Python is trying to be sort of a language that does everything. And I think that explicit is better than implicit. Kind of like one of the problems with object-oriented programming is that it is sort of by definition oftentimes making things implicit. So I think some of the implicit like nature of trimesh is due to its object orientedness, which you can't fault it for it too much because that's kind of what people are used to at this point. But you don't have to write object oriented code that works that way. It's not requirement. You could not required. You can build very complex systems that that don't do that. Let's call this parts match. What is mode here? Mode, edge mode, unknown projection mode. Yeah. Okay. So let me set up a little bit of a test for this before we start, just to make sure that we're on the right track. And yeah, and writing Google style doc strings. Yeah, I one quirk that I have is I don't I'm not a big fan of complex doc strings. Some people go crazy with like return types and stuff, or and it's like I think that should just be pretty obvious from the arguments themselves what the arguments mean, and you can just write a prose description in the doc string. Okay, let's go back to here. And so actually we'll just leave this off and not generate it for now, just to save a little time. And for the parts that we're going to match, we we're going to do circle of radius like 50. This needs to be a little big, maybe 25, and set equals tau divided by 4, and sub is 3, and we will attach y coordinate of this of like 30 or something, and let's I don't think, do I forget if I don't think I have a way of viewing a mesh with markers or anything on it. That would be something good to add. I could do spheres. That wouldn't be too hard. So, as And we will take a look at this. Matches with colors. Going to look at the fuselage with kind of a gray. And let's see here. Oh, nice. I already have that. Right. And then translate X sphere to Y with makeup red. Okay. So we should see our points here that we're going to try to project. There's what our sphere model will look like. Okay, yep. So here's our 3 spheres. I'm going to actually, yeah, I'm going to nudge these forward a little bit more. Just to get them away from that. Actually, you know what? I do want rays. Yeah, I do want rays. I don't want just closest point. I want rays because I want to be able to project down. Because I'm certainly going to know... Wait a second. Huh? I have to think about this now. This is like, I want to find basically where the hard points sit. Like right on the surface. You know what? I think... No, I think I do. I think I don't want rays. Because I want to do... I think I want to do... Yeah, I don't want rays. I want nearest because the things I'm going to be measuring from are mostly going to be offset by the normal of the panel. Gosh, it's a little gotchas like this. Okay, and we're gonna also throw a debug exit after that, so we don't have to sit through all this. Okay. Okay. Yep, and we're gonna nudge this forward a little bit. Okay, so and we can make this radius quite a bit smaller. Smaller, not bigger. Okay. Okay, so if we use our current method, let's just make a little function here. This. I guarantee you I wrote this exact same thing somewhere else, but who knows where it is, so. Okay. So now we're going to project our points. Points projected. Decap dot find intersections. Find proximity parts with parts. And I don't think the fuselage is shifted. Actually, we can do better. So we can actually flatten parts into mesh like this, and then that'll be safe and for sure correct. Okay, so we're gonna find the proximity to the parts here with our original method. Points to project. Mode is going to be decal mode face, and this returns multiple things. So it returns the points and distances and normals, which we don't need right now, so we can ignore. And we'll look at this. So does the original method do what we want? And let's get rid of this. Yep. And yeah, it does. Okay. And we can get rid of this. Okay. So just to show that again, we've got our points. A little bit off the surface, and then we find the nearest point on this mesh. Okay, so that's our original method. What we want now is we want a new method where we're not only going to do that, but we're going to find the original part, and we have the capability to map that point back to the coordinate system of that part. So how is this going to work? Well, let's take a look at this. So instead of flattening the parts into a single mesh, and let's just get rid of this mode because we don't need that. Okay, so instead of flattening into a single mesh, we're going to flatten the parts into a dictionary of the part name and the mesh. And yeah, so we're actually going to do global transformations. Yeah, there's going to be a little bit of redundancy here, but that's okay. So meshes is going to be and transformations. These are both going to be dictionaries, I believe. Okay, so now we are going to do this proximity finding where we this is the face, triangle indices. Yep. Okay. Okay, so we're going to build a new dictionary that's keyed on the mesh name. So for aim mesh in meshes. So we'll find proximity with all the points. And I'm going to do this like this. And I'm going to not worry about normals, because I think yeah, I'm not going to worry about normals. That's fine. Okay. What we're mainly going to be interested in here is the distances. So we're going to store all of this stuff in res. Now, for each point, we're going to find the nearest, or the one that has the smallest distance across the parts, and that's going to be so we have a dictionary here that's for each part. Oh no, YouTube decided to drop network. Yeah, everything looks good on my end. We're going to make a map for each point. So actually we'll call this part to prox, and then this will be this. So this will be keyed on index. So for index in range points.shape 0, oh, statistics panel's network activity dropped hard to 0. Interesting. Okay, so now we want to look across all of the meshes, or all of the things in part to prox, and find the min. So we want to basically find let's see, so like d min float. I just forget how to do float. Forget how to do float max in Python. Float INF. Okay. So okay, so we can also just store this here, I think. Okay, so this name, and actually we just want to store actually res of index. Actually, yeah, res can just be a list, and this can just, we'll just initialize this to be none times shapes. Actually, yeah, sorry. We don't need to get this fancy. So x plus none, x min equals oops. So this is just going to be pulling out surface of index. This is index. Let's see, and this is face. Did I forget? Oh yeah, you're right. Values, good catch. I've been using Python professionally for like 10 years now, and like every day I forget what you have to iterate over for a dictionary. Usually it's that I forget the dot items. Yep, that is, yeah, you're right. And see, I did it again. It's items. To me, the natural way to iterate over a dictionary would be that if you just like iterate over it with no method, it should iterate over keys and values together, like items. Like items should just be the default. Like I understand, if you're gonna test in, like if you test like a key in a dictionary, that should be fine. But it's very weird to me that by default it iterates over keys instead of tuples of keys and value. Okay, so now at the end of this loop, we're gonna have the results, so we can append. We can append it. All right, and actually we want the name of the part to go in here too. Okay, so now what we can do is we could do the transformations in here. I don't think we're gonna do that. I think yeah, we don't really need that here. I think we're gonna do that outside. So let's go back up here. Okay, so this is now going to be a list of things. Yeah. I think that's one of the big problems with Python, is that too much, it's like supposed to be its own thing, but too much of it kind of depends on the C implementation. It's very hard to get away from that in the language, and that's okay. But Okay, so now we're gonna have a set of points that are still in the global coordinate system. So if we do something like this, we should see roughly the same thing. So if we flatten the parts and then we take the What is it? Let's pull this over here. We have name. So it's like the second thing. Oh no, these are, yeah, these should still be global. So this should still work. For X. Let's see what this does. Yeah. Oh, I didn't actually return the result. Classic. Okay. Okay, that seemed to work. Now, what we should be able to do is we should be able to look at these things locally. So let's loop over this. And actually, let's just destructure it right here. So we've got name, point, and a couple other things that we don't care about, right? Yeah, the distance and the face index. I suppose we could do the face. We could grab the face index. Do something interesting with that. Now, so here's what we want to do. So we want to find these global transformations of the parts, and then we want to take and we want to view mesh with points. But instead of the thing, we're gonna want the part. So we're gonna take the part by name and grab the model, and then just gonna look at one point at a time because we're finding one part per mesh, and this is going to be parts.transform point inverse. I think it's the inverse, right? Because we're taking we're taking a global to local. Forward would be local to global. So we're taking it point and the trans of name. Now, let's see if we did this right. And if we did, I think this might be a good stopping point for tonight. Yep. Look at that. Okay, I'm going to look this over again. So you can see we've got these little points hovering over this panel, right? Our original projection method just takes them there in global coordinates. We don't know which point they belong to. Now we can do the same thing again, but we actually are aware of which part, and we can get the location in that part's local coordinate system with that transformation. Let's add a whole bunch more parts just for fun, and I'm going to add a TQDM on this just for fun, because this might take a while. Start taking a little longer with more parts. Oh, interesting. This is gonna cause some interesting behavior because I think it's gonna should actually hit the drives. But yeah, so we've got a bunch of parts. Yep, you saw the progress bar go. Yep, there we are on that drive, that drive, that drive. All right, okay, that is working. It's kind of late here, but basically we have the positions in the local coordinate systems of the parts now. So at this point, we can do this kind of constructive greebling that I was showing based on these points in the global coordinate system, and the points that we'll end up using is like the hard point locations or the shield ring locations, right? Those will be like very close to the surface, but that'll help us find where they belong for those panels. So yeah, some exciting stuff here. Some kind of heavy duty stuff, although I'm kind of proud that I had all of the pieces ready to go to be able to do this. This code is going to need a little bit of cleaning up, but overall we had a good start. I'm just going to play with this a little bit more. Okay, go bigger here. We could even oops. So there's a issue. Like if we don't have a actual if we don't have a transformation, then what's going to happen? I don't know what's going on. I bet what was going on there was that it said it was finding the fuselage as the closest one. Let's actually let's just increase the radius. That should fix that. Yeah. Oh, nice! Look at it. It found the ends of the antennas. Nice. And that's gonna be right in the middle. Found points on the hard points. So probably something that I'll want to do is like exclude certain things, right? So like, for instance, and I don't think I have a specialized filter, but I could just say like I could exclude certain things. So can filter out hard points. Make sure that we're always projecting onto oh, that's interesting. What gives? Oh, that's the original method. Yeah, here's the method where I'm excluding hard points, and we go right down onto the panel. Or I could like say keep the fuselage, but only do panels. You know, what I should probably do is I should probably add some kind of functionality where I could say I want to keep this subset of the parts, but keep the hierarchical material that's required to get those um, parts. Or actually, I could probably just filter after I found the global transformations too. That would be another way to do it. I could add a filter function to the part finding. But this is basically exactly what I want. So I'm gonna call it here and rest on my laurels. But thanks everybody for coming by and hanging out. I really appreciate it. It's a lot of fun. Um, it's a lot of fun to work on this and hang out with you guys. Thanks, Doug, for coming. Thanks, Jupiter BJY. Hope you can come back and um, we can do some more of this. And you should live stream some of your Python uh, coding as well. It's a lot of fun, and it's kind of fun to put yourself on the spot sometimes. So see you guys later. Thanks again, and have a good rest of your night.